second in the series of Provost's graduate student lectures this semester. A very excellent and diverse set of lectures. I'm sure Jacques will attest the competition to pick out the applicants was a pretty difficult job for us on the selection committee, and we tried to balance scientific excellence with a broad representation of the diversity of graduate student research on this campus. And I'm happy to introduce today's speaker, Betül Pamuk from the Department of Physics, who's going to tell us about the thing we really need, which is how to understand the properties of water, which of course is essential for life. And I'm going to turn over this then to our advisor, who will do a better job than I can of introducing Betül.
Thank you. So I think most of the people here already know Betül. Betül has been working with my group. I just learned, because I don't remember that well, since the summer of 2009. Right? 10, okay. So, and actually I'm trying to keep her in the group as long as possible, because we are so going to miss her when she leaves, not only personally, also scientifically right now, really, we depend on her so much. And she's been doing an outstanding work on studying water, not that much liquid, but the glassy and icy forms of water. And she actually has, what's the core of her presentation today, which is related to the anomalies of water. And yesterday when she rehearsed, she didn't say this, but in the list of anomalies of water, there were 68 anomalies, and now there's 69, because Betül's paper actually put one new one on the list. So actually that was one of the greatest achievement of her paper, and she's going to talk about that today. So thank you, too.
Thank you, Marvi. Thanks for the introduction. So today I'm going to talk about the importance of quantum mechanics to understand the properties of water. And when you hear the properties of water, we have been with water for so long. Don't we know everything about water already? And my answer is that if you look at the Science magazine, in 2004, one of the breakthroughs, they listed the top 10 breakthroughs of the year, and in the list of runners-up, one of the questions was how water works. The next year, Science magazine, again, was celebrating its 125th anniversary, and they made a list of top 100 questions from all over the sciences. And one of the questions that they still see an open question, an unanswered question, is what is the structure of water? And at the time, there was a big debate about how many bonds each water molecule makes with its neighbors. Now we are starting to have a better understanding of the structures of water, but some of this debate still continues. And why there is such a big debate? It's because water is such an anomalous material. One of the anomalies that you're familiar with is that ice floats on water. And you know that from a hot summer day, you go home and you drop a cube of ice in liquid water, and you see that it floats. And why that's the case? Because as water freezes to ice, the molecules start to become ordered in a hexagonal phase. That's why you see snowflakes in the shapes of hexagons. And as it freezes, it expands to form these hexagons, and it starts to have these voids in the middle. And to form those voids, it expands, therefore it becomes less dense, therefore it floats on, ice floats on liquid water. And if you go to this website, now it lists, including my work, 69 different anomalies of water. Well, we don't have the time to go through all of them today, but I'm going to mention some of the hot topics of today. And one of the hot topics is anomalies in supercooled water. So if you look at the phase diagram of water, you see as we change the temperature from the liquid phase, we get to the ice. This is the same hexagon ice that I showed you before. as we decrease the temperature, liquid becomes solid. However, if we decrease the temperature very carefully, and if we have a very pure water, then we can have liquid water below freezing temperature. And that phase is very metastable, and it's called supercooled phase. Now, why this is important? Because water has these three anomalies that one of them is the isothermal compressibility. Any material, if we decrease the temperature, its compressibility decreases. Normally, the materials shrink as we decrease the temperature, and as it shrinks, it becomes less compressible. In water, at 46 degrees Celsius, we see a minimum, and then as we get close to the melting temperature, it starts to increase, and if we get beyond melting temperature in the supercooled regime, it diverges. A similar thing happens for the heat capacity. In any material, it goes linearly down. In liquid water, we see a minimum, and then as we get close to the melting temperature, it starts to increase. In supercooled regime, it diverges. And same thing happens for thermal expansion. It normally decreases linearly, whereas in liquid water, we see that density maximum is at 4 degrees Celsius, and then it diverges in the supercooled regime. So people were curious how the phase diagram looks in the supercooled regime, and they started to hypothesize about this. And how we do is we have the stable water, and then as we decrease the temperature very carefully, we start to have metastable liquid, which as I explained, is called supercooled water. And as we keep decreasing the temperature, we cannot keep supercooled water stable anymore. We start to have crystallization of ice. So we cannot do liquid experiments in this region. If we go from below, if we freeze water under pressure, we can have a glassy state, which is an amorphous state, which is disordered. It doesn't have the hexagons that I showed you for regular ice. It's disordered, but looks more like liquid water, and we call it amorphous phase. And it's down here. Now, it has high density amorphous, and as we decrease the pressure, we get to a low density amorphous phase, and there is a phase transition between the two. But if we increase the temperature, at certain point, we cannot have liquid water. We directly get to a crystallization to ice. And in this between, we call it a no man's land, where we cannot make liquid water experiments. So we cannot reach the liquid state in that area. So people started to debate how we can explain these anomalies in the supercooled regime and what is going on in this no man's land. And the debate is if there is a high density liquid, like in the amorphous phases, and low density liquid in this no man's land, if there is a phase transition between the two, and if there is a critical point between the two. And how we hypothesize this is using computer simulations. So to do computer simulations, we need water models. So in a very classical picture, this is my water molecule. We have oxygen, hydrogen, hydrogen. And we put, in a very simplistic picture, we put the negative charge on top of oxygen. We put a positive charge on the hydrogens. We fix the bond length, the intramolecular bond length. We call this covalent bond. We fix that distance, and we fix the angle between the hydrogens, and we can start running simulations with this model. But this is an oversimplified picture of water. Instead, we know that the negative charge is not on the oxygens. It's slightly away from the oxygen, and we call these lone pairs that has negative charges around here. So the next simplest thing that we can do, instead of putting the negative charge on the oxygen, we can put it on these lone pairs. Okay, let's improve our model a little bit more. Another thing that we can do, we can, instead of fixing these angles, we can put springs between these atoms and let the angle, let the hydrogens oscillate between these two, and let's put a spring between these two bonds and let that spring change the bond angle. So this simplistic picture has a harmonic oscillator-like behavior. It has a very simple intermolecular potential. And those parameters that are the bond lengths, the charges, and angles and everything are adjusted so that they will reproduce experiments in a certain point in the phase diagram. We don't have one single model that will work very well all through the phase diagram of liquid water to ice to everything. So, but the advantage of having these models is that we can simulate large number of atoms. For example, if anyone works in the life sciences here, biophysicists can simulate, use a lot of molecules of water because they simulate DNA in liquid water. And there they need to simulate large number of atoms, therefore they need this simplistic picture. And these simulations, because they have a simplistic picture, they're very fast. We can simulate them in our computer for a long time and obtain better statistics with them. But they're computationally very cheap, and I can run them on my desktop. But they're not very accurate. So what I do instead, I want to convince you that quantum mechanics is important for these calculations. So I do quantum calculations. And I don't want you to see anything in this equation except the fact that this is a very general equation. It doesn't depend on any parameters from liquid water. It has no fitted parameters to reproduce experiments. This is a general equation that works for any molecule, any atom. Now, it's a very high-level equation, and I can solve only part of it exactly. And there is a certain part that I cannot solve exactly, so I do approximations to that part. And because it's very accurate, it's computationally very expensive, so I need supercomputers to run those calculations. And this is a picture of a small cluster that we have in our lab. Now, in this level of quantum calculations, we don't see charges as point charges, but instead we see them as electron clouds. And this is what one of my molecule would look like. There would be a negative electron cloud around here and a positive electron cloud around here. And when, so this is one of my molecules. When the hydrogen of one molecule points towards the oxygen of the other molecule, we see that there is a binding interaction. And this interaction is called hydrogen bonding. And hydrogen bonding is the key interaction that holds water molecules together to form ice and liquid water. And this is what the hydrogen bonding energy looks like. As we change this distance, we see that around 3 angstroms there is an attractive interaction between the two. So next, I look at the, but to understand hydrogen bonding in liquid water, it's very hard because liquid water is very disordered. So instead, to have a better picture of hydrogen bonding and what's going on, I look at a simpler picture. Instead of looking at liquid where everything is disordered, I look at ice. And I start by looking at regular ice. This is the ice that you have in your fridge and the ice that you have to deal with on a cold summer winter. But instead of looking at it in a macroscopic level, I look at it in a microscopic level. I look at the molecules and I simulate them in my computer. And this is the structure of hexagonal ice. This is the same structure I showed before. The oxygens are sitting in a hexagonal symmetry, and the hydrogens can point in any direction they want, except each hydrogen, let's have a look at this one for example, should be bonded to its own molecule, and it should be pointing towards the oxygen of its neighbor. And each hydrogen makes a well-defined hydrogen bond in ice. So, and this is the rule in ice. This is ice rule. We call it ice rules. So all hydrogens has to obey these ice rules. Every hydrogen has one bond, covalent bond to its own molecule and makes a hydrogen bond to its neighbor. Okay. But before I go ahead and explain to you everything that's going on in ice, I want to give you a brief introduction to harmonic oscillator. And this is because I want to differentiate between the classical models where we have springs between the atoms to quantum models. Okay, in a classical harmonic oscillator, let's say I have a ball and it's attached to a spring and it's oscillating back and forth. Its potential energy would look like a valley. And the energy of my particle would depend on the temperature. Depending on how high or low the temperature is, it can take any energy value along this line. And when it oscillates between these two hard walls. Now, we're interested in looking at this because at high temperatures, we associate high temperatures to classical energy. So for high temperatures, classical harmonic oscillator is important. But as we go at lower temperatures, then quantum harmonic oscillator starts to dominate. Let's see what happens in the harmonic case. Again, I have the same shape of a valley for my potential. And then, instead of my particle taking any energy along this line, it takes quantized energy levels. So my particle starts to have a wave-like behavior. Now, these energy levels, so my particle cannot take only certain energies, and that's determined by this En. Let's see what happens at low temperatures. If we have a classical particle, as we decrease the temperature, now we get to the bottom of this valley, and so its energy is zero in a classical particle. However, for a quantum harmonic oscillator, when n is zero, I still have a finite energy, which is labeled here. So even at zero temperature, my quantum energy has a finite energy level. And that energy depends on the frequency of the oscillations. And the frequency of the oscillations depends on the mass of the system. As the mass increases, frequency decreases, or vice versa. Let's look at this relation in a little bit more carefully. Again, I have my quantum well, and then I have my classical energy, which is determined by the temperature. Now, if my mass goes to infinity, that means my frequency is zero. That means I'm in the classical zero energy. But as I decrease the mass, the frequency increases, so my quantum 0 point energy starts to become visible, but it's still lower than the classical energy. So at this picture, the classical energy dominates. Let's see what happens if I start decreasing the mass and increasing the frequency. As the mass decreases, the energy starts to increase and the frequency starts to increase. So from going to a classically dominant picture, we get to, as the mass decreases, to a quantum energy dominant picture. This energy starts to become very important. And I'm explaining all this because hydrogen is the element that has the lowest mass on Earth. So for hydrogen, this is the hint that 0 point energy is going to be important. Okay. And why am I explaining all this? Because there is an anomaly in ice. Okay, let's first explain what happens normally. Let's look at neon, which has a similar mass to water, and what happens normally. At high temperatures, all elements in nature can be found in different masses. Their electronic structures are exactly the same, but their masses are different, and we call these isotopes. So here we're looking at two different isotopes of neon. One has mass 20, and one has mass 22. At high temperatures, we cannot differentiate between the volume of these two masses. But as we decrease the temperature, now the quantum energy starts to become important because now my temperature is below the quantum energy. And we can differentiate between the two isotope volumes. And the lighter isotope has larger volume than the heavier isotope. Okay, let's see what happens in ice. At high temperatures, I can already start to distinguish between different isotopes. One has larger volume than the other. And this is true even at the melting temperature of ice. As I decrease the temperature, I see that the heavy isotope, which is called deuterium, it's just has a special name, that's heavy hydrogen, the ice with the heavy hydrogen has larger volume than ice with regular hydrogen. And this is opposite to what we see in neon. So what happens that makes the heavy isotope with smaller volume and light isotope with large volume? As I explained in the harmonic oscillator, we see that if we have a light atoms, they vibrate a lot. So they vibrate with a high frequency and high amplitude, and they're like the Tasmanian devil. They're all over the place. However, if we have heavy atoms, they're like Cartman. They're fat and chubby, and they don't like to run around much. So they're very localized. Their frequencies are much smaller, and therefore their volume is smaller. Let's see what picture this gives to us for one water molecule. Here we have hydrogen with the light atoms. For the same oxygen, we have larger hydrogen atoms. Therefore, one water molecule with hydrogen has larger volume. Whereas if we have heavy hydrogen isotopes, deuterium, then deuterium has smaller volume, and the overall water molecule has smaller volume. Wait, this is opposite to what I was just explaining you. Then why the regular ice with deuterium has larger volume than light ice? I was talking about hydrogen bonding from the very beginning. Let's look at what happens if we have other materials with hydrogen bonding. This is another material, you don't need to know anything about it, another material that has hydrogen bonding. So if we change from hydrogen to deuterium, we can differentiate between the volume of the two at low temperatures, and deuterium has larger volume, just like in water. But when we increase the temperature, we cannot differentiate between the volume of these two. So ice is extra anomalous if you want. But the key is the hydrogen bonding. So what happens is that is related to the vibrations in ice. If you look at one water molecule, it can make different type of vibrations. It can do asymmetric stretchings. It can do symmetric stretchings. It can do bending. Or it can do librations along different axes. Okay, so when we have a hydrogen that's vibrating between these two molecules, it has a larger volume and it's vibrating a lot. That makes the hydrogen bonding between these two molecules very strong. And the covalent bond within the molecule weak. Whereas if we have a deuterium, it's small and it's localized close to the oxygen, which makes a strong covalent bond, but in opposite, it makes a weak hydrogen bond that determines the distance between the molecules. And the distance between the molecules determines the volume. Therefore, even though the molecule itself is smaller, the hydrogen bond is weaker, and the overall volume of ice is larger when we have deuterium than we have hydrogen. Okay, so let me show you how I calculate this. What I do is I calculate the electronic energy of the system quantum mechanically, and on top of that, I calculate the vibrational energy of the system. But looking at the vibrational energy itself is not enough. I need to look at how this vibrational energy changes with a change in the volume. And that is defined as the Guernsey parameter. I don't want you to remember any of the equations from this slide, but I want you to remember that if we have normal isotope effect, positive Guernsey parameter is dominant, and if I have negative Guernsey parameter dominant, then I will have anomalous isotope effect. And here are my results. I'm showing you the exact same thing as before, as the cartoon that I had before. We are looking at the change in the volume as a function of temperature. And the dots are the experiments, and the lines are my calculations. Let's first focus from hydrogen to deuterium. As we increase the mass of the hydrogen, there is an increase in the volume that agrees with the experiments. That's anomalous, and that's about 0.1%. Okay, if we did not include any of the phononic vibrational energies, that's the volume that we would have. So from the volume without phonon energies, vibrational energies, to the real quantum volume, we have about 1% expansion. Remember that I talked about neon before, which had similar mass. There, this difference is 12%. So why is it so tiny in ice? Okay, in ice we don't have only hydrogen, we also have oxygen. So let's see what happens if we change oxygen, which normally has mass 16, to oxygen, which has mass 18. Then, from this black line to green line, we decrease the volume. So we have normal isotope effect. Again, we have the hydrogen here, and we increase the mass of the hydrogen to deuterium, and we increase the volume. However, when we increase from oxygen to oxygen 18, we decrease the volume. So there is a competition between normal and anomalous effects in here. And as I emphasized before, at high temperatures, both experimentally and my calculations show that there is a divergence between the deuterium volume and the hydrogen volume. So it's a small effect, but it's an effect that's due to a competition between normal isotope effects from the oxygens and anomalous isotope effects from the hydrogens. And okay, I want you to focus here first. We're going to look at this picture, the zero temperature picture. These are my quantum volumes that are higher than my classical volume. And that's what we're looking at here. We're looking at the same thing, volume, as we change the mass of the oxygen and mass of the hydrogen. Blue means low volume, and red means high volume. And this is where my regular ice is. As I increase the mass of the oxygen, the volume decreases, and I have the anomalous isotope effect. As I increase the mass of the hydrogen, the volume increases, and I have the anomalous isotope effect. And as I increase mass of both of them and go along this diagonal, I get to the classical picture where the volume is smaller than the quantum volume. This is at 0 Kelvin. Let's look at the same thing at 200 Kelvin. From the previous picture, 200 Kelvin is here, and the classical volume is larger than the quantum volume. And we're again looking at volume, and we increase the mass of the oxygen, and we have normal isotope effect because volume decreases. And we increase the mass of the hydrogen, and we have anomalous isotope effect, volume increases. As we increase both volumes, we get to the classical limit where classical volume is larger than the quantum volume. So if you do not include quantum effects, that means that we are either going to underestimate or overestimate the volume of the real system, and we won't calculate it properly. And how we calculate it is, again, I'm showing you the same vibrations that I showed before. These are the asymmetric and symmetric stretchings of the covalent bonds, and their energies. They have high energies. And here, I'm showing you the Guernsey parameter, how they depend on the volume. And remember, negative Guernsey parameter meant anomalous isotope effect. So the frequencies with high energies have negative isotope effect. If we go to low frequencies, these are signatures of the hydrogen bonds, and they have positive Guernsey parameter. Therefore, there is a competition between the positive Grunizer parameter of the low frequencies and the negative Grunizer parameter of the high frequencies. There's a competition between the covalent bond and the hydrogen bond. And this is similar to the picture I explained to you before. In regular ice, the covalent bond was weaker and the hydrogen bond was stronger. And in D2O, the covalent bond was very strong and the hydrogen bond was weak. So because of this competing unharmonicities, we have the anomalous isotope effect. Okay, so let's see. So this is the quantum calculations. And at the beginning, I talked about water models. Let's see how they behave, how they predict if we are going to have normal or anomalous isotope effect. I'm going to show you two different types of water models. And one of them is designed so that it will reproduce this top picture for liquid water. And let's see if it's going to predict the isotope effect. And we see that H2O has larger volume than D2O. So it predicts normal isotope effect. It does not correctly reproduce it. And this is because reproducing the vibrations is not enough. You also need to reproduce how those vibrations depend on the volume. So they also need to reproduce the Grunizer parameter correctly. Let's look at another model. This model is a little bit more advanced because it can change the charge and the bond length and the bond angle. And in this model, at low temperatures, we see normal isotope effect. But as we increase the temperature, we see anomalous isotope effect. So we recover the anomalous isotope effect only at high temperatures. So water models are improving, but they're not there yet. They still don't have the correct amount of unharmonicities in them. Let's test water models for one more thing. I told you that in a regular ice, the hydrogens are disordered as long as they obey the ice rule. As we decrease the temperature, the hydrogens lock themselves at certain positions and they become ordered. And we call this ordered phase ice 11. And from experiments, we know that for low temperatures, this is the stable phase. Let's see if my quantum calculations and the water model that I just showed you can predict this hydrogen ordered as the stable phase of ice. Here we're looking at the energy difference between the two, and the quantum calculations show that hydrogen ordered phase has lower energy than the hydrogen disordered phase. Therefore, hydrogen ordered phase correctly predicted to be the stable phase. And we actually see a phase transition between the two. For classical models, we see that they do not reproduce the correct stable phase. They show that the hydrogen disordered phase is the stable one. And there is a tiny energy difference between the two. So there is still room for improving water models. But ice is not that simple. Up till now, I only showed you hexagonal ice, the regular ice, and ice 11, the hydrogen ordered phase. Here you see the hexagons. But as we change the temperature and pressure, we have 13 different phases of ice. So we want to understand what happens as we increase the pressure and get to ice 8, where all these voids are completely filled. And to do that, we looked at several different types of ice and ice-like systems to understand the effect of density on the volume. First, we looked at these structures called clathrates. They are cages of water molecules. Here I am only showing the oxygens for simplicity. And these are stable structures under high pressures. Next, I look at two amorphous phases of ice. These have no order. They're like the glassy states that I was talking about at the very beginning. They look more like liquid water. And what these plots show, for example, if I have one oxygen, the next oxygen, the next nearest neighbor of the oxygen will be, let's say, around here. For this one, you see there is a bump here. The next nearest oxygen will be very close to the first one. So this one has low density, and this one has high density. So these two phases are low density liquid like amorphous phase and high density liquid like amorphous phase. And finally, I looked at ice 8, where it's one of the most densest phases of ice. Okay. Here I'm showing you the vibrational modes. Again, cloud rates look very similar to regular ice. And then for LDL and HDL, low density and high density liquids, we start to see that we cannot differentiate between the stretchings of the two anymore. So they look more like liquid water. And ice 8 has a very pronounced stretching modes. But as I explained to you before, looking at the phonon modes is not enough. We also need to look at how those phonon modes depend on a change in the volume. So we need to look at the Gruneisen parameters. And to do that, we calculated the Gruneisen parameters, and for cloud rates, for all of them actually, for low frequencies, we have positive Gruneisen parameter dominant, which is like the hexagonal ice. But for low frequencies in cloud rates, they're very much like hexagonal ice, and they're very negative. In low density liquids, they are still negative. As we get to high density liquids, we start to see a mixture of positive and negative, and it's getting close to 0. And for ice 8, to show these, I really had to zoom in here. We have some negativity, but they're almost 0. Okay, so how does this Gruneisen parameters show the anomaly versus normal isotope effect? In cloud rates, as we look at the volume as a function of temperature, we see that deuterium has larger volume than hydrogen, so it has anomalous isotope effect. And we know that cloud rates are stable under pressure, and there are experiments done on how this volume changes as a function of pressure for different isotopes. Those are these dots here. And the lines, which are my calculations, agree very well with this isotope effect prediction. But one thing we realized is that cloud rate has a very similar density to hexagonal ice. So it looks, so the anomalous isotope effect is true for low density. Let's look at the low density like amorphous states. There we see that we have anomalous isotope effect again. D2O has larger volume than H2O all the way through. And these still had negative Gruneisen parameters. As we get to high density like amorphous phases, we see that we start with a normal isotope effect, where a heavy isotope has smaller volume than the light isotope. But as we increase the temperature, we see a crossing, and the heavy isotope starts to have anomalous isotope effect, and we see a mixture of normal and anomalous isotope effects. As we get to ice 8, there, the Gruneisen parameters were almost 0. They were not dominant anymore for high frequencies. And we see that we have normal isotope effect, where the light isotope has larger volume than the heavy isotope all the way through. And we know that ice 8 is stable under pressure, so we looked at it at high pressure, and we still have normal isotope effect. So I showed you a variety of different ices and ice-like structures, where we started with a very low density ice and went from hexagonal ice to cloud rates, low density amorphosis, high density amorphosis, to high density ice 8, and we see a transition from a negative Gruneisen parameter dominant phase to positive Gruneisen dominant phase, from an anomalous isotope effect to normal isotope effect. Now, our ultimate goal is to understand what happens in liquid water. And the future direction that we're going to is to look at how the volume changes as a function of temperature for different isotopes in liquid water. And even in the liquid phase, at high temperatures, we can differentiate between these two isotopes. The quantum effects are still there, and they are still anomalous. And if you look carefully, you see that at low temperatures, the difference between these two volumes is large. But as we increase the temperature, this difference between the volume decreases, and that's what you're seeing here. But at some point, so we start from a low density phase of ice, we start to melt, so my liquid is more low density liquid, and as I increase the temperature, it becomes high density like. And then these start to deviate again, so we see a minimum here. And we think that it's linked to the isothermal compressibility minimum that I showed you at the beginning, at the very beginning. It's the same, that is, as I decrease the temperature, I see a minimum in the isothermal compressibility. As it becomes very highly densely packed, it's harder to compress. So there is a transition from, we think there might be a transition from low density to high density, and there might be a link between the two. So that's the future directions. With that, I'd like to summarize that we have looked at the vibrational zero-point effects for a variety of ices from low densities to high densities, and we saw that there is a transition from an anomalous isotope effect for low densities to normal isotope effect for high density ices. And we think that we can link it to liquid water and how the volume of water changes as a function of temperature, and we hope to link it to the compressibility of liquid water. And I'd like to thank my advisor, Mariví Fernandez-Serra, Phil Allen, he is my co-advisor. We had a lot of good discussions with him. Peter Stevens did experiments for heavy oxygen. There were no experiments known to us before that. So he made our prediction, he showed that our prediction is correct, so he made our work very strong. Jose Soler is Mariví's close collaborator in Spain. We had good discussions with him. And Luana Pedrosa is our postdoc. Whenever I had a question, she was always there to answer me. And I'd like to thank the rest of my group, and I'd like to thank you for your attention.